Welcome to my talk with Fabio Tiritico. Today, our topic is about retrofitting your legacy Java app with a reactive flow pipeline. Here's our agenda for the day. First, we'll do an introduction, and then we'll talk about enterprise JVM applications from the 2000s, so a bit of history. And then we'll move on to discussing about some of the complex problems as to why we're proposing this approach. And these problems are happening in this ever-evolving, very complicated computing world. And then we'll then propose our solutions using the reactive approach. And then at that point, Fabio will then do a demo of what we're proposing with a pipeline. And after that, then we will have a conclusion and discuss some of the important key points that we learned from this exercise. But first, let me give an introduction. My name is Mary Grugleski. I'm a senior developer advocate at IBM, doing Java, open source, DevOps, and cloud these days. I'm also the president of the Chicago Java Users Group and a few other technical communities in the Chicago area. And now we have Fabio.
Hey, welcome everybody. Thanks for attending our talk. And my name is Fabio Tiritico. I come from Italy, but I'm based in Amsterdam. And my Twitter handle is TicoFab, which is a lot easier to pronounce than my family name. And I work as an engineering manager now in Amsterdam, but I also run the Reactive Amsterdam meetup, where we discuss, all things reactive, so reactive systems, reactive programming, all of that. So in case you are ever in this area, hopefully we're going back to do live event soon. Please join us. And back to Mary.
Thank you, Fabio. Okay, we'll start. So let's discuss a bit about some traditional enterprise JVM applications. So we've heard the word microservices, but it really goes back to the origin of why we do microservices was because in the Java world, applications used to be monoliths. They all run within the same, even like same JVM space. You can have the whole, essentially the whole system, let's say an e-commerce. You can have order system, kind of shipping, the payment processor, all of these things. The main part, they are all running within the same container, or actually a JVM. But as you can see too, having a system like that can be very expensive in the operational sense, because while it is, maybe you can think of the fact that there's not as much to worry about network have to worry about that connecting all of these components because they run in the same space. But the fact is that if you need make any changes to any one aspect of your system, let's say you want to change something in the payment system, but nothing else changed, but because they are all existing within the same larger container, this VM, then you actually have to stop everything and then introduce the new change and then have everything restart again. And so as such, the thing is, the whole operational aspect becomes quite complicated. You need to coordinate with all the different pieces. And so what it used to be too is that in an enterprise team, you will have separate teams doing development and separate teams doing the operational part. And a lot of coordination is needed. As a result, too, it's actually high maintenance cost, too. It's less agile on the development side. If we need to introduce changes, we have all these paperwork to do. And it's just not, able to scale too well in the modern, especially in today's world with doing cloud native, when everything needs to be a lot faster, a lot agile, and that, any changes needs to happen quicker. And so not only that, too, the fact is, in such a complicated world, we're also working with many different parts that needs to be all moving at the same time in their own pace, but they need to all kind of come together in a very orchestrated, very coherent kind of manner. So in that sort of concurrent processing world, the traditional way of doing things are just not able to meet, today's standard. And then another thing too is that the recovery part too also can be complicated, because anytime if something goes wrong, then again it affects the whole system. So as you can see too, like the list goes on, and while there are some benefits of it because it makes kind of like a little bit easier to do, again, with the communication between different components. But the fact is, the whole kind of thing is like running a three-legged race. When you kind of trying to do stuff, you need to all run at the same pace, and that's kind of an expensive operation. And so again, we brought up some of these complex problems, right, in this ever-evolving world, highly distributed systems that we're dealing with now. I don't think that there are any systems in this world, especially in this internet cloud-native days, that are not distributed. Everything is operating in a very distributed, very concurrency-centric, concurrent, kind of processing is like everywhere. We don't want to have the traditional way of doing things in which you need to block. Essentially you need to issue a request and then you sit there and wait for the answers to come back. And that's the idea too, is that we need to make sure asynchronous processing is happening. And not only that, if in smaller systems it's probably not an issue, but in larger systems, when you have so many asynchronous data flowing everywhere, you need to also have mechanisms of controlling back pressure, for example. So these are like some of the complex problems that we have to deal with, and we kind of like been thinking about how the best way is to handle this kind of situation. So the solutions we're talking about here is really using a reactive approach. And of course, too, in today's cloud-native environment, we're also talking about microservices. And microservices, too, it's an architecture that doesn't dictate how you do it. You can definitely do it the reactive way. The reactive way, again, it deals with data streams, and also, too, it handles back pressure very well. And also, too, is the asynchronous, event-driven type of approach that kind of fits more closely to the model that we have, as we live. So in a computing sense, the reactive approach is actually a very good way of helping to solve some of these problems today. So as we can see, right, microservices, they're agile and very small piece, bite-sized kind of functionality. And then also, too, the DevOps aspect, too, it really helps, too. So then it eliminates the need for huge, like, operational teams to do all of the work that's necessary. And also, too, in terms of release cycles, too, it also helps with, like, quicker release cycles, too. And then, of course, ultimately, too, it's also the asynchronous side of processing that allows for concurrency, but without worrying about the mechanics of a lot of the threading concerns, because we are now letting the libraries take care of some of these threads. What it used to be in the kernel space that you're kind of holding up processing because it's only like one thread doing things, but now essentially all the threads are being done on the user space now on the reactive library side. And then with that, we kind of have our proposal of this solution of how to kind of retrofit some of your legacy applications. So we'll have Fabio come in here and show a demo.
Yes, thank you very much, Mary. What you're seeing on the screen now is indeed a little demo that we packaged and published for you, and we're going to go over it. Basically, just as a very quick overview, we're going to simulate, these two legacy processors that we have. The pipeline, if you read it from left to right, you'll see that the first legacy processor ingests some data from a Kafka topic, and then does some processing, passes it on to the second legacy processor, which after some processing will publish the results on a second Kafka topic. And what's important to know really here, not only the shapes are important, but the arrows connecting them are really key here. What we have chosen is communication methods between all these pieces that basically use back pressure all the way from the very beginning to the very end. And by doing so, we leverage on Akka Streams for the first legacy processor, which is a streaming framework, as a streaming tool from Lightbend, available for Java and in general Scala, the JVM languages. And the connection between the first legacy processor and the second one is via RSocket. So RSocket is a protocol that sort of it's a direct competitor of HTTP, let's say, but it's built already with the streaming and back pressure semantics in mind, as we're going to see in our demo. So let's jump into. I'm going to share my screen, and so we'll jump into the demo. There we are. You should be seeing my browser now. I just wanted to point you to this repository on GitHub that contains our demo. You can see there are 4 folders here. Each one of them contains one process, except infra. Infra contains really there's a Docker Compose file that we will use to spin up locally our Kafka backplane. And then we have the 2 legacy processor, and this sources producer is really just a tiny process that will insert some data in the first Kafka topic, so to trigger the entire thing. We're going to be we will share this URL later, so you can check it out. Okay, so let's start up our infra using Docker Compose. Docker Compose now. So now we are creating the Kafka broker. There it comes, and once it's ready, we can start our sources producer little process. This little process is just going to basically push items 1 per second on our Kafka topic. So here we are. You see it's creating 1 message per second and publishing on Kafka topic. And now, before we launch the 2 legacy processors, I want to just give a brief look at the code. Starting with the first legacy processor. You see, it's not very long. It's a couple of files. This one is the files, is our main, let's say. It's a Scala app, actually. And these are the lines that bring everything together. Before this, once we are, creating some configuration about the consumer, we are creating the RSocket sync. So what's going to happen here is that we will start reading from the Kafka topic, all these messages 1 by 1. We are doing some process with them. This is the legacy processing logic that we have encapsulated, let's say, in this project, in this process. And then we are going to push the outcome of the processing onto the RSocket sync, so that they will be actually ready to be read from the other side, the RSocket source on the second legacy processor. So let's give a look at that. This is our main class of the second legacy processor. This is a Java application. And there's two main points here. First, this acceptor is the place where we define the logic of what are we going to do when we receive some payload from the first legacy processor. And what we're going to do, defining this function, is we are going to basically take out the data from the payload and do some processing. This is, again, simulates our legacy processing. And then the result of this processing, we are going to put it on our second Kafka topic. So this will be basically the end of our pipeline. Now, what's important to notice here is that at the end of this processing logic, there is this line, return flux.empty. Now, the RSocket Java implementation is based on the project Reactor. So if you are familiar with Spring and Spring Boot and that sort of environment, you will feel right at home. You will be very familiar with the Flux and Mono objects. In this case, we are returning this flux empty object at the end of our processing for each message that we receive to signal upstreams that we're done. So if we don't return this, before returning this, the producer of data is not allowed to send more data downstream. After we're done doing whatever we're doing here, we can signal upstreams this message saying basically, okay, I'm ready to process a new one. And this is really the basic of back pressure, is where a consumer can basically dictate the rate of the producer. Now, after looking at our logic, the rest of the code here is really just about putting all the pieces together, creating a RSocket server that listens on these ports, and that's it basically. Let's try and start this thing then. What I want to do is first start our legacy processor 1. Now, what's interesting to see here for us is that here we are. The legacy processor 1 has started fully, and it's in this phase under the hood, it's trying to connect to the second legacy processor, but there's nothing to connect to because we haven't started it yet. So this guy here is actually, because he hasn't received any message from downstream allowing it to process something, it's actually not consuming events from the first Kafka topic either. It's just waiting. Basically, up until the moment where the second legacy processor gives us, let's say, permission to start processing data, that's the moment where we will start seeing something happening here. So let's get there. Let's start this the second legacy processor. All right, so now the second processor is up and running. The first one has found it, and it started sending it down messages. And what I want you to see here is something funny. As you can see, this second legacy processor is taking some random times to process messages. So I'm just simulating that it takes some time. And as you can see, when the second legacy processor is busy processing, the first one doesn't do anything. It's not like it's reading all messages and pushing them down regardless. It's waiting for that flux.empty signaling message that you saw in the code. And so you see now it's processing. When it processes for 1 second, it's quite quickly, sometimes for 4 seconds. And this guy, the first guy, just stops and waits. And this is really crucial, because when we are going into encapsulating, retrofitting our legacy processes, you want them to be able, to cope with load and sort of protect them from maybe new load. Maybe your business has scaled up. In the meantime, you need to consume more traffic or something like that. Well, these ideas of having, streams that are fully back pressured is your best guarantee to keep your service alive in the cloud, up and running, without overwhelming it and potentially crashing it because of too much load. So I would say that the reactive tools that we are given nowadays are really, really good to encapsulate our legacy processors. This one last little thing I want to show you in this demo is if we see this RSocket sync. What is it? If I go inside the code of this class, basically Akka Streams, remember this streaming engine that I mentioned in the beginning that the first legacy processor is based upon. It lets you create connectors to lots of different things. So in this case, I wanted to create a fully back pressured connector to RSocket. And so in here, you can see the logic that I used. It's documented. So for instance, when we start, at the very beginning, when we instantiate this object, we will execute this pull call. This pull call is basically, again, in back pressure terms, we are telling upstreams that we have capacity to handle the next item. And so then later, when we are allowed by downstream to push one item, we will push this one item that we requested from upstream. So by doing this grab, we access the item that we just pulled earlier. We grab this payload, we push it downstream using the R socket that we created. There it is. And then later, when we get a request, remember that flux.empty in the second processor, when we get that sort of request, we're going to pull another one from upstream. So you see, everything is connected this way. And with this, that concludes my small demo. So I am going to stop sharing my video and we can go back to the slides. Yeah. So what's the experience that we had in building this pipeline? Pros and cons. Well, first of all, again, as I said, the Reactive Streams standard enables different technologies to work together thanks to this back pressure standardized approach. But in my experience, different implementations are not yet very easy to get to work together in the same process. So what I mean is, for instance, our socket is based on Project Reactor, which is an implementation of the Reactive Streams. Akka Streams is also an implementation of Reactive Streams. So in principle, they could work together, but making that happen is not as straightforward as it should be. Not yet, at least. Our socket per se is a very new and promising technology. I really, really like it. But of course, it has all the perks of relatively new projects. Documentation is very scarce. There are some examples, but of course, there's just example. Maybe they don't show exactly what you need. And also, the Java implementation relies on Project Reactor, as I mentioned. So, you might not like it. It might be perfect for your case, but maybe you don't know it, you don't like it, you don't want to learn it. But in this case, at the current moment, you are forced to use it if you want to use RSocket, the RSocket Java SDK. And finally, while HTTP has not built for the purpose of creating back-pressured streaming pipelines, there are some HTTP implementations with underlying streaming semantics, like Akka HTTP provides one. And that could be a faster, more accessible way to modernize your application rather than studying an entire new protocol like RSocket. So do keep both in mind, though, because RSocket, I think, has a great future ahead. And with that, I pass it back to Mary.
Sure. Thank you so much, Fabio. I think it's great. Yeah, that the example is small enough, but it really illustrates a lot of the the key things that we need to pay attention to if we're doing like implementing a pipeline, right? Using these different implementations. And it's also, you can see, I think the code too is kind of very elegant too, as you can see with the functional style, the reactive stream. So I really like it.
Thank you.
So, thank you. Yeah. So yeah. So now I think then we come to our end, towards the end of our presentation. We'd like to kind of summarize and give a conclusion. So what are the findings, right? Some alternatives, and then we'll also talk a bit about Project Loom. So I think that, as we can see, using a reactive approach, I think it's something that we feel it's definitely, gives a lot of opportunity in helping to solve problems in this concurrency space with dealing with large amounts of data that you need to process them all at once, coming from different sources and stuff. So, and the thing is too, is that it can handle the back pressure. You can essentially rely on the reactive streams, because all these libraries are supporting reactive streams. It can handle back pressure very well without having had you to kind of worry about it. So let the libraries themselves do the work for you. This kind of important things in a concurrency type of scenario. So and then we also kind of want to kind of talk about if there are any alternatives, I think, to this approach, or what do you think? If we don't use reactive, do we have any other approach to help with handling, say, back pressure? You think, Fabio, or
I wouldn't know. I mean, I'm also the wrong person to ask because I run the Reactive Amsterdam meetup, so I really like reactive stuff.
Yeah, that's right. Yeah, to me, I feel too. Yeah, reactive. To me, when I'm looking right at all the solutions out there, I feel reactive. It's a newer kind of kind of approach, and maybe like less clear to a lot of folks. But I really feel if people take the time to understand it, it's actually definitely is the alternative to consider to helping with,
especially on the JVM. Reactive Streams has been officially part of the JDK since JDK 9 already, so definitely right. Give it a look.
Give it a look. That's right. Okay. So now, then also there are questions that came up now, right? What about Project Loom? So Project Loom originally was scheduled to be delivered in JDK 18, but I think right now they're not clear, not 18, but definitely in a future release. So what about Project Loom, right? I've heard myself, and I'm sure Fabio too, we talked about it, that people came and said, oh, Reactive's going to go away because of Project Loom. I really don't think so. I mean, I kind of share my feeling is that Project Loom handles, kind of their native implementation and their handling of, or kind of a lightweight mechanism of doing threads now. They're using fibers, kind of sort of like coroutines in kind of Kotlin too. It's a bit, lighter weight, and it's easier to kind of handle like concurrency. But the fact is it handles all of these lower level kind of mechanics, right, in dealing with threads. So has kind of not solving the same kind of problems that a reactive library is dealing with. Reactive libraries are a higher level for your application, though not the highest level, but the fact is they each have different concerns. So then to me, I think it probably what we will see is that reactive library is going to be retrofitted to use Project Loom fibers at some point. Rather than saying that one take over the other or wipe out the other. But what are your thoughts too, Fabio, on that? So
yeah, absolutely. Project Loom will allow basically asynchronous programming to become sort of invisible, and use it with your classic imperative style of programming without worrying about async, await, or promises or things like that, futures. Project Loom will make some of that transparent. But yes, it doesn't solve the architectural issues that you will have. So yes, your project, your single process will become probably more efficient, non-blocking in many different ways. But how do your services interact with each other? That's a whole another story, and you still need to deal with that.
That's right.
So I think that, like Mary said, they will complement each other very well.
Yeah, exactly. So so that's our conclusion about this, and I hope sincerely everybody would consider using this approach of, if you can identify parts of your application, legacy application, can kind of extract out certain data transformation using the pipeline. I think will be a very good choice that you'll have. And with that, I think it comes to our end of our presentation, and here are the links to the things that we've talked about on our code, Fabio's GitHub, and the Reactive Manifesto, Akka Streams, our socket, the protocol. And also, one note is to point out about Quarkus too. Quarkus comes out of Red Hat, and they actually, it's interesting too, you can actually do imperative and reactive coding within the same space. That's kind of an interesting cloud native ready kind of modern infrastructure for cloud native. So, and then also, there are also links to Docker as well. Yep, and then with that, thank you again. And here are our contact, various contact information, our Twitter handles, our LinkedIn profiles, and GitHub and blogs. And I myself also have a Discord server if you'd like to continue the conversation as well. And I'd like to also ask you to sign up for the free IBM Cloud if you like. So with that comes to the end of our presentation. And thank you so much for coming to us and join us today. And
thank you very much indeed. Thanks, Mary. You too. Thank you.
Thank you. Thank you.
Bye.
Bye-bye.